The heart of the Raycaster is the DDA march. Each iteration, the hardware compares the accumulated X and Y side distances to decide which grid boundary the ray hits first. If side dist X is smaller, we step along X. Otherwise, we step along Y. In Verilog, this is a simple combinatorial comparison. The side register records which face was hit, which the radar phase uses later to create a shading effect. The loop repeats in hardware until a wall tile is found. This is a section of the control logic of the pixel stream generation module. What this is doing is it stores the heights of the next walls in the next heights buffer with 720 indexes as the DDA is doing ray by ray. So when the DDA has done each ray, it will load it into the relevant index in this next heights buffer. And then this is a section of the control logic of the pixel stream generation module. What this is doing is it stores the heights of the next walls in the next. This was a visual bug we found in early development. From analysing wire values in a simulation waveform and their expected values, we determined that the bug was caused when rays with near vertical or horizontal direction grazed against the wall. To fix this, we made all near vertical or horizontal rays only move in that X or Y direction. This locking procedure fixed the issue. Here's the overall block diagram for FPGA. Moving back from the HDMI, we can see the HDMI block in the bottom right, which is driven by an axis stream by the Raycaster. This Raycaster can then access, via memory addressing, the BRAM in the BRAM gen block just above the HDMI block, and to the left of that we have the BRAM controller, through which the PS can write through player direction, player position, sprite position, and map data into the BRAM for the Raycaster.
The engine ships a general-purpose hardware UI overlay, so any game on the platform can define its own interface without touching the bitstream. 3 IPs chain inline on the pixel stream. Text boxes and fill bars are pure combinatorial logic, one cycle using no memory. Text reads from a glyph BRAM where each pixel clock the hardware computer row address, fetches a byte, and selects a single bit. The whole system costs under 180 LUTs and 1 BRAM tile. The default PYNQ pipeline writes every frame to DDR3, 900 kilobytes, 55 megabytes per second, and frame rate tied to the ARM. We removed the VDMA entirely. The VTC runs on a fixed pixel clock, so frame rate is now hardware locked. Tearing is impossible, and a full 55 megabytes per second is freed from the network.
The server is a single-threaded async I/O reactor decomposed into 4 stages connected by lock-free queues, inspired by SCDA, staged, event-driven architecture. The key insight is that the hot path is I/O bound, not CPU bound. There's negligible computation per tick, so threading would just add lock contention and context switches for no throughput gain. What SCDA gives us is isolation. Each stage only talks to the next through a queue, so it's the structural benefits of stage decomposition: back pressure, isolation, independent testability, and clean observability, without any of the locking overhead you'd normally pay for.
The UDP receiver is essentially the datagram protocol callback. It receives 24-byte datagrams from the PYNQ ports. No parsing, just on queues the bytes. It returns immediately, so the event loop never blocks it. T2 is the game tick. It runs the authority logic. This consists of sequence validation, wall collision clamping, tag detection, and ghost AI. It also builds the packet game state and fans out to 2 independent queues.
T3 is the broadcast stage. It awaits the broadcast queue and fans out the authoritative game state to every connected node via send2. That's it, no computation, just delivery. The reason it's its own stage is isolation. If a send2 blocks momentarily, kernel socket buffer full, that back pressure stays in T3 and never pushes T2's tick deadline. The queue absorbs the jitter, and because it's a separate coroutine, we get independent observability.
T4, the Redis writer, is the persistent stage. It takes the game state that T2 produces each tick and writes it into Redis, which is our hot tick store. It pulls from the write queue, packages all the H-set operations together into a single Redis pipeline, and flushes that once per tick. So instead of n individual round trips to Redis, we get one batch call. T4 is the only stage that runs on its own OS thread rather than as a coroutine on the event loop. The reason is that Redis writes are blocking I/O. Even though they're sub-millisecond, if you put blocking calls on the async I/O event loop, you stall T1, T2, and T3. The other key thing T4 does is act as the boundary between the real-time loop and the persistence layer. To access the monitor and the server statistics, we run the PYNQ dev bash script, which SSHs into EC2 with a port forward on 8080. It drops us straight into a team-up session that auto-launches the game server and the monitor. All our packets are custom struct pack binary, no JSON. These run at 60 Hz, so overhead matters. Fixed size means no framing. 3 of our most key packets are on screen. You'll notice the naming. Node packet is camel case, the others are PKT prefixed. That's deliberate. Node packet comes from the client. It's named as a data class because it represents the node's own state. The others are all server-originated commands. The convention tells you at a glance which direction it travels. All our packets are custom struct pack binary, no JSON. These run at 60 Hz, so overhead matters. Fixed size means no framing. 3 of our most key packets are on screen. You'll notice the naming. Node packet is camel case, the others are PKT prefixed. That's deliberate. The following slides include live clips from the monitor, which isn't just a dashboard, it's a game development environment. The map editor lets you paint 32 by 32 arenas with brush fill and line tools, place spawn points and push that design straight to every node's VRAM in real time, so you draw a map and instantly playtest it. You can configure AI entities from the monitor too, tweak their behavior traits and drop them into the arena without restarting the server. The live top-down view tracks every node in real time. Players, AI ghosts, all on the current map geometry. And the video on this slide also shows the game logic in action. You can see tagging events and spawn, resets happening live. So you're not just observing the game, you're authoring and iterating on it. That's what elevates this from a monitoring tool to something closer to a game dev IDE. On the PYNQ side, aka the client side, it's just a Python script. We SSH into the board and run launch.py, which loads the bitstream onto the FPGA, initializes the VRAM and button GPIO, opens a UDP socket to the server, and drops into a 60 Hz stick loop. Persistence is 3 tiers, and the core principle is isolation. The game loop never waits on the database. Redis is the only tier the real-time path touches, sub-millisecond. Batched pipeline writes from T4 every tick. That's the boundary. Everything beyond Redis is asynchronous. DynamoDB is 5 to 20 milliseconds per write. That alone exceeds our tick budget, so it's completely decoupled. A separate sidecar process drains Redis via BRBOT and writes to Dynamo at matched replay end only. Those writes run in the background thread, so even the sidecar's own event loop doesn't block. S3 is 50 to 200 milliseconds. Compressed replay uploads via multipath, even further from the hot path. So the isolation is layered. T2 never touches Redis directly. That's T4's job on its own thread. T4 never touches DynamoDB. That's the sidecar's job in its own process. Each hop adds another buffer between the game tick and slower I/O. A 20 millisecond Dynamo write or a 200 millisecond S3 upload physically cannot affect the player.
We have 2 parallel stacks, PYNQ and SIM. They share the exact same set of logic, but the client side is different. The PYNQ stack talks to real boards over UDP. The SIM stack replaces the hardware with Python scripts that fake board inputs. Same protocol, same packets, no FPGA needed. This is crucial for parallel development. The hardware team can be working on the bitstream and the board client, while I'm iterating on game logic, persistence, and the monitor, all from a laptop using the SIM stack. Neither side blocks the other. Then when we plug in real boards, nothing changes server side. This is button to live, visible, multiplayer, gameplay data. The full round-trip player experiences. Button press on the PYNQ board to new frame rendered on the monitor. 35.7 milliseconds. The top bar is button to visible, and the bottom is raw round-trip time. Look at the difference. That thin sliver in the middle. That's the entire server. T1, T2, and T3. 1.7 milliseconds. 5% of the total. The network owns the other 95. Now here's everything else the server does. Redis writes, monitor WebSocket pushes, DynamoDB persistence, S3 replay streaming. Notice the scale, 33 milliseconds for the monitor push, 45 for S3. These would destroy the tick budget if they were on the game loop, but they're not. Every one of these runs in a separate process or thread. Here's a queue metric we use throughout testing, queue depth over time. If a stage falls behind, its queue grows. 10 seconds, 2 boards, 2 AI goes. Full load. All 3 flat near 0. Every stage drains faster than work arrives. That's not just the architecture working, it's proof the queues are balanced. Producers and consumers will match.